Understanding of the HPLC technique and understanding about the HPLC chromatogram is very important, and it is required for the pharmaceutical field. We should understand how to interpret the HPLC graph. It is also called as chromatogram, as it is a result of the chromatography technique of analysis. How to interpret an HPLC graph or chromatogram. Welcome dear viewers to this short video, and in this video we will learn regarding the HPLC chromatogram. HPLC graph is also called as or known as chromatogram, and it is a plot detector response on y-axis versus retention time on the x-axis. So these two terminologies are very important to understand: detector response on y-axis and the retention time on x-axis. First, we need to understand these two axes. X-axis provides you the retention time in minutes. It means retention time means time taken by each component or compound to elute from the column. Understand that HPLC is a column chromatography, and retention time is a time taken by the compound or drug or material or substance to come out from the column. Y-axis provides you the detector response, and it provides the understanding about signal strength, usually UV absorbance if detector is UV, related to the compound concentration. Now understand and identify the peaks. Each peak corresponds to a different compound in your sample. That means different samples will provide you the different and distinct peaks. First peak to appear generally represent the most polar or non-retained compound. So it depends on to the gradient. It also depends on to the type of HPLC, whether it is normal or RP HPLC. So first compound is generally considered it as a polar or non-retained compound. That means it is coming out at the earlier. Latter peak represent more retained compounds. That means these compounds which are coming out in the latter stage, these are spending more time into the column. So these might be less polar or with higher affinity for the stationary phase. As in the HPLC, we know that two phases are there: mobile phase and the stationary phase. Mobile phase is liquid, stationary phase is solid in the column. Then key parameters in the chromatogram. So here you can be able to see the response versus retention time, and three peaks are there. First is impurity or excipient. This is just to understand you, make you understand about the peaks. First is impurity or excipient peak, second is the main peak, and third one is the degradation product. So these peaks are well resolved, and the middle peak is the API peak you can consider. Key parameters in the chromatogram. Retention time, it is denoted by the RT, time at which a peak elutes. It helps to identify the compound. That means retention time is specific for the compound. Peak area, it is proportional to the amount or concentration of the compound. Then peak height, it also correlate with amount, less accurate than the area. Resolution, it is represented by RS. Resolution is a measure of separation between the peaks. RS more than 1.5 means good separation is there. So separation should be there, resolution should be there. Tailing factor indicates the peak symmetry. Tailing 1.2 may indicate issues. If tailing is more than 1.2, it may be showing that tailing is there, and it may indicate the issues. Baseline noise, it indicates system suitability. High noise means poor sensitivity. So system suitability should be good, and system suitability, resolution, tailing factor, then retention time, all these are done activities in the method development. Then peak retention time, area, percent area, and interpretation. So peak 1, 2, 3 we will understand. Peak 1 is coming at retention time 2.45, area is 3000, percent area is 10%, interpretation possible impurity or excipient. Then peak 2, retention time is 5.22, area is 25,000, percent area is 83%. Interpretation, that is main API peak. Then retention time of the third peak 7.4 minutes. That means it is coming out at the late stage. Area, it is having area of 2200. Percent area is 7%, and non-degradant product it may be. So it depends on to the method development. In the method development, we characterize each compound, its retention time and its area depending on to the concentration. So impurity or excipient at 2.45 minutes, main API peak at 5.22 minutes, degradation product or degradation impurity at 7.4 minutes. So this is the hypothetical graph to make you understand about the peaks in the chromatogram. Now compare with the standard. So match the retention time of sample peaks to standard peaks to identify the compound. That means standard standard material will have some retention time, and you match the retention time to the standard peak. Use calibration curves like area versus concentration to quantify the compounds. Check for system suitability. Retention time of standard is consistent. Theoretical plates, that means if it will give you idea about efficiency that meet the system criteria. Tailing factor and resolution, these are within the acceptable ranges. Now common issues in the HPLC graph. So there may be tailing, there may be broad peak, there may be ghost peaks, noisy baselines, shifting retention times. These issues may come in the HPLC system and in the HPLC graphs. So we should understand what are the issues and what are the causes for these common issues. So broad peaks indicate poor column performance and overloading. If peak tailing is there, it uh, make you understand regarding secondary interactions or column aging. Ghost peaks, that means carryover or contamination. Noisy baseline, that means detector issues or mobile phase impurities. So each peak in the chromatogram gives you information about something. We should understand it and we should interpret. Shifting retention time. If there is change in the retention time of compound, it indicates that there is a problem in the flow rate or temperature. So issues are there and causes are there. And based on these issues and causes, we should make the possible remedies to solve those problems. Now coming to understanding about the detector response. So detector response in HPLC, it refers to the output signal produced by the detector as it measures the concentration of analytes like API, impurities, degradation products as they elute from the column. Then as the material or compound elute from the column, in the column it gets separated from the matrix and then it comes out of the column. Once it comes out from the column, it is detected by the detector. Detector provides the response. So detector response is typically plotted on the y-axis of the chromatogram, and this detector response is measured in milliabsorbance units, that is MAU, when using UV visible detector, which is one of the most common detectors in the HPLC. Some other detectors are also there, and it will provide you the detector response based on that detector. For UV, it is milliabsorbance units, that is MAU. Example, if a peak has a height of 100 MAU, it means the detector registered a light absorbance signal corresponding to that magnitude that at that particular retention time. The area under peak, that is MAU, is often used for the quantification of analyte. The area under the peak is often used for the quantification of the analyte. In practical terms, we will understand the higher and lower detector response. Now, higher detector response means stronger absorbance is there, higher analyte concentration is there. And if lower absorbance is there, that means there is a weaker response or lower analyte concentration. So depending on to the detector response, we should understand about the absorbance and the analyte concentration. Now, how the detector response affects or is impacted. Detector response depends on the concentration first thing, because as the concentration get increased, the detector response will provide you the peak. The concentration of the analyte, the wavelength selected specific to the analyte's absorbance. The type of detector may be UV detector, PDA detector or RI detector. So we should understand that the detector response is affected by concentration and the wavelength. Key points to consider detector response is that it is not a absolute concentration but a relative signal proportional to the amount of the substance passing through the detector. Coming to the interpretation of HPLC graph. So whenever you get a HPLC graph, consider and focus on retention time, peak area and the resolution. There should be separation between the different peaks and peak component and the matrix component. If resolution is not good, that time you should say that or consider that the method is required to be altered or developed once again. Then compare with the standards and calibration curves. Use it to identify, quantify and evaluate purity or degradation. HPLC technique is most widely used technique in the pharmaceutical analysis, and it is used for the various tests like testing the potency assay, testing the impurities, dissolution and many others. So we should know and understand the HPLC graph. We should know how to interpret HPLC graph and what that HPLC graph is saying us. In simple way, I can say that what that graph is saying. We should hear that, we should interpret it, and then we can do the uh, or we can do some research, we can do some exercise to find out the problems. Thank you for watching the video.